Hey there guys, Mr. Hames here, and today I'm going to talk about kinematics. Kinematics is the branch of mechanics concerned with motion. Okay, so we're talking about words like displacement, velocity, acceleration, time. Kinetics is the study of forces. I'm going to talk about a little bit about this next week. Today we're focusing on kinematics, so the study of motion. Before I get started, I just want to quickly touch on units. Units aren't actually that hard, guys. We use unit conversions in all fields of science, and so it's really important that you get this under your belt. So, and there's a pattern that forms kilo, mega, giga, tetra, 10 to the power 3, 10 to the power 6, 10 to the power 9. And then if we go the other way, obviously we've got like centimeters here, but let's just not worry about them for now. We've got 10 to the power negative 3, 10 to the power negative 6, 10 to the power negative 9, 10 to the power negative 12. So these are sort of the values that these units always abide by. Okay, if I'm going from, let's say, grams to kilograms, oh sorry, these are just the units. Obviously there's heaps more units out there. I've just chose some common ones. We've got grams, meters, and liters, and they all go by the same rules. If I want to go to grams to kilograms, kilograms values at 10 to the power of 3. Okay, so I actually have to divide by 1,000 because obviously grams is smaller than kilograms. Kilograms is bigger. As you can see, it's 10 to the power of 3, so it's bigger. So we need to divide by 1,000 if we're going this way. Again, if we want to go from kilo to mega, we divide by 1,000. And again, to get to giga, we divide by 1,000 again, and so on. You get the idea. And to go the other way, we times by 1,000. So obviously 10 to the power negative 3 is smaller than 10 to the power 0. So we need to times, again, times by 1,000 and times by 1,000. And you get the idea. So to go from milli to micro, we need to times by 1,000. To go from micro to nano, we times by 1,000. If we want to go from nano all the way to mega, we have to divide by 1,000, divide by 1,000, divide by 1,000, divide by 1,000, divide by 1,000. That's 5 lots. So we need to divide by 1,000. So 5 lots, so 10 to the power of 5, 10, 15. Okay. And if we add this negative 9 and 6, we would get that 15 figure. So whenever we're moving right on this table, we need to multiply. Whenever we're moving left, we need to divide. One thing I also want to touch on is this idea of length. So if I have meters squared and I want to go to kilometers squared, obviously these units have been squared. So if we're going to convert units from meters squared to kilometers squared, we actually have to square our value that we're multiplying by as well. So if we're going from meters here to kilometers, usually we would divide by 1,000. But because our units are squared, we also have to square this value. If we're using volumes, so let's, for example, we've got, let's go kilometers cubed, and we want to go to meters cubed, we would have to times by 1,000 usually to go from kilometers to meters, but because this is cubed, we also have to cube this value here. So have a bit of a study on that. We really need to get that sorted under our belts. Now, scalar versus vector. Scalar does not have direction. Vector does have direction. So that's the difference between scalar and vector. They both have magnitude, okay? So both have magnitude. but vector has direction. And we can represent vectors with arrows. Arrows have magnitude, so how long it is. So this arrow here has less magnitude than this arrow, and direction, because obviously it points somewhere. So when we're talking about distance versus displacement, a lot of students say, aren't they the same thing? No, distance is scalar. It does not have direction. Displacement is a vector. It does have direction. In the same way, speed versus velocity. Speed is a scalar, whereas velocity is a vector. Velocity, again, has direction. Speed does not. Then finally, we have acceleration, which is also a vector. Another pet grime of mine, speed equals distance over time. A lot of students like to use this triangle. I don't like it. You're going to use your mathematical skills that you have spent hours practicing in mathematics. If we're going to transpose this equation, t is on the bottom. To cancel out this t on this side, we need to multiply by t on both sides. So see our times t here, you'll notice that they cancel out. Whatever you do to the right, you need to do to the left. So I get speed times time equals distance. And again, if we were to get time by itself, if we wanted to get time by itself, we could then divide by s on both sides. Notice that these cancel, leaving just t by itself. So t is equal to distance divided by speed. Now, the next step in terms of, so we can rearrange our formula, fine. We have done that all through our schooling life. But another thing students struggle with is units. If I have distance here, and distance is usually in meters, you have to look at the question to check that. And where we don't know what the units of speed is, time is usually measured in seconds. So if you're plugging into your formula a distance value with meters and a time value of seconds, then what's the units of this speed going to be? There's a simple way to work it out, guys. If you're dividing meters and seconds, notice our units will be meters per second. Meters on the top from our distance, time on the bottom. Time on the bottom is seconds, distance is at the top, meters. So if we're using meters in our formula and seconds in our formula, our units for our speed will be meters per second. Who would have thought? In the same way, we can do this with any equations. So if let's for example, concentration is equal to mass divided by volume. If we're using, let's say, grams for our mass, and we're using, for our volume, we're using liters, then our concentration will be grams per liter. Easy as that, guys. Grams at the top, liters at the bottom. Grams per liter. Another example might be, so for example, if we use distance instead of meters, we use kilometers, and then for time we use hours, then our units will be kilometers per hour. Okay, because that's what we're using in our formula. So in this way, we can work out the units in a test by simply using your formula. If we were to rearrange this and get speed times time equals distance, and we're trying to find our distance, and the question gives us kilometers per hour for our speed, and time as hours, then when we times our speed times by our time, you'll notice that things start to cancel. The h's cancel out, and it leaves us with just kilometers. So in the same way, if a question gives you kilometers per hour for your speed, and then gives you only minutes or seconds for your time, you'll notice that the hour does not cancel out with the seconds now. We have to convert to hours. Okay. So hopefully that helps you out a little bit. I would like to go through that a little bit further in class time. All right, we're getting to our graphs now. So this is where we talk about kinematics. We've got displacement on the y-axis and time on the x-axis. So if I just draw a line, what does this line actually mean? Well, you can see that the displacement is increasing and the time is also increasing. Okay, and the information that we can get from this graph, so let's just say time here is 10, and then we've got our displacement here as 10 meters, so this is 10 seconds, then you can tell that in 10 seconds, this person or whatever this object is traveled 10 meters. All right. Now, if we work out the gradient of this line, gradient is equal to rise over run. So our rise will be change in displacement. So change in, so I can, this is a delta, it's just like a triangle that explains change in, so this is change in displacement. And then I've got change in time. And you'll notice that displacement over time looks very similar to speed equals distance over time. So displacement is at the top and time is at the bottom. So in summary, the gradient of a displacement time graph is actually speed or velocity. Okay, so velocity again is the vector form of speed. Okay, and if we want to work out the units of the gradient, for example, if we use seconds for time and meters for displacement, well then if we plug that into our gradient, meters divided by seconds, we get meters per second. And these are the units of velocity, change in distance over time. Now we move on to a velocity time graph. On our y-axis we have velocity, on our x-axis we have time. In this graph here, I've just drawn a straight line. If we want to work out the gradient is equal to change in velocity divided by change in time. if we want to work out the units, so let's just say velocity is in meters per second and then time is in seconds, we get meters per second on the top and we've got seconds on the bottom. And this actually is the same as saying meters per second per second. So it's the change in velocity over time. And if you already notice, meters per second is the same units for acceleration. So acceleration is the change in velocity over time. So if it's speeding up, we have a positive acceleration. If it's slowing down, we have a negative acceleration. And the units is, so this meters per second is the velocity per unit of time. So we get meters per second, or you'll see meters per second -2, which means the same thing. It's the change in velocity over time. So that's what the gradient in a velocity time graph gives us. So the gradient gives us acceleration. And in a test, if a test says, what information does the gradient give in a velocity time graph? Well, then you'll go back to Mr. Hames's example and be like, oh, let's just work out the units. Velocity is meters per second. Time is seconds. If I divide meters per second by seconds, then I get acceleration. So you can actually work out the answer without even memorizing it. Now let's work out the area under the graph. The area under the graph. If I was to work out this area, I would have to multiply velocity by time. So if I multiply velocity, meters per second, times time, you'll notice that the seconds cancel out and I'm left with just meters. So that means if I work out the area under a velocity time graph, then I'm actually working out the displacement. All right. Finally, acceleration time graph. Got a straight line again. As we said before, acceleration, the units of acceleration is the change in velocity over time, which is meters per second, and time is measured in seconds. If we were to work out the gradient of an acceleration time graph, I would have meters per second divided by seconds, because we divide the y by x, rise over run, and we get meters per second. This doesn't actually give us much information. It just gives us the change in acceleration over time. Okay, so we don't typically work with this unit. But there is the area under the graph. For the area under the graph, I have to times the x-axis by the y-axis. So I get meters per second times by seconds, and this will actually cancel out one of the seconds. So we're left with meters per second. And the unit of meters per second is change in distance over time, which is velocity. So the area under the graph of an acceleration time graph will be velocity. So I've done a little bit of a summary here for you. So this is the graph type, displacement versus time. The gradient gives us velocity. Velocity time graph, the gradient gives us acceleration. Acceleration time graph, there's not really much information it gives us. Area under the graph of a displacement time graph doesn't give us much information. Velocity time, we get displacement. Acceleration time, we get velocity. Now, you can memorize this table, or you can use the skills that I just taught you to work it out yourself. You don't need to know this table to work out what velocity time, what the gradient of a velocity time graph is. Well, you know velocity is meters per second. You know time is seconds, so if we're working out the gradient, you get this. And you know that meters per second gives us acceleration. So you can work it out yourself, guys. And in the same way, in a test, if they give you tricky units, you'll be able to work out the units without guessing them. So this kinematics, this idea of kinematics and how these different graphs are related to each other, it's actually getting into what we call calculus. You don't need to know this, but just appreciate next year in methods, you're going to be talking a lot about calculus. So this is sort of a precursor and a sort of idea of how these graphs are related. So you'll notice that, let's just focus on this little part of the graph here. So this is a constant slope. Okay, if you have a constant slope, that means your distance is increasing at the same rate. So the change in distance over time is constant. The change in distance over time is constant. Okay, this means it has a constant velocity. So if you have a straight part on your graph of a distance time graph, that means you have constant velocity. So if you work out the velocity using the gradients of this graph, you'll notice in a velocity time graph, a constant velocity is actually just a straight line. It's a straight line because the velocity isn't increasing. There's a constant velocity. And then if you translate that to the acceleration time graph, the acceleration is 0 because the velocity is constant. Okay, so you can see through these three graphs how they're related. So let's talk about when there's not a straight line or a constant gradient. This part of the graph here, increasing slope indicates increasing velocity. So the increasing slope indicates increasing velocity. You'll notice that it's getting faster and faster and faster. Okay, and this translates to an increasing velocity on our velocity time graph. If velocity is increasing, that means there's acceleration, and the acceleration here is constant. Okay, so for every unit of time, so we're talking about meters per second here, every second there's an increase of 4 meters per second. Then you'll notice that the graph starts to decrease, okay? The gradient starts to decrease over time. This means it's slowing down because we're traveling less distance per unit of time. So you'll see here the velocity is starting to decrease. Okay, velocity is starting to decrease. This results in a negative acceleration. Okay, so if it means we're slowing down, there's a negative acceleration. And then you'll notice that at this point here, we're not actually moving, okay, because we're not increasing in distance. So we've at a standstill, which means that there's 0 velocity. And obviously if there's 0 velocity, it means there's 0 acceleration as well. So hopefully you can sort of understand or start to appreciate how these different graphs are related to each other. So that's about it, guys. I know I went for 25 minutes, so apologies for my talking. If you have any questions, please ask.